3 goals today. First, we made a mistake yesterday. I want to fix the mistake. And it was not a mistake of mathematics. It's a mistake of conception of our problem. That mistake, however, is going to be corrected. And when we do correct it, it's going to add a whole bunch of other things that you probably didn't think about that we need to connect together. Second, there is no conversation in physics there's no conversation in physics that doesn't include a discussion about energy. And there's clearly energy in orbits, and we're going to have to come to a discussion about how we deal with energy in orbits. And like anything else, we have something that's spinning. There's probably going to have to be a conversation about momentum and angular momentum too. So we did a brief discussion yesterday about orbits. We talked about elliptical orbits and we talked about circular orbits. We did some circular orbit work yesterday. We calculated the period of oscillation for what? The Earth-Sun system and maybe the Earth-Moon system. Let's talk about where we made our mistake. If I take an object and just throw it, based on what we talked about 2 units ago, you're supposed to remember that regardless of what the object's shape is, and it could be some object shaped unsymmetrically, that it will naturally revolve about its own center of mass. You guys remember that conversation? All right. The Earth-Moon system behaves the same way. In fact, all orbiting systems behave the same way. Which means yesterday, when we calculated the period of rotation of the moon around the Earth, we actually did it wrong. Because we assumed that the moon revolved around the center of this system, meaning the center of the Earth. But that's not what happens. What actually happens is the Earth and moon revolve around some point in between. Not sure where this point is. It's got to be somewhere in between. I think it's probably closer to the Earth than it is to the moon. So before we can actually calculate the real period of the moon, we're going to have to figure out where the center of mass is, which is something that I thought just saying it would mean you guys could launch into some work and do it. But what I found was not the case. But I'm still going to give 7th period and Edison the benefit of the doubt. Because he said, he was enthusiastic. Yes, I believe I can do it. Or he was, yes, I believe I'll need somebody to help me do it. But I'm going to start with giving you the benefit of you are smart, learned people. And it's on the equation sheet. You will need information that I do not believe I provided to you. So you tell me what information you think you would need in order to make this calculation, and I'll give it to you. What's that? You will need the masses of what? All right, well, I gave you the mass of the Earth yesterday, but if you don't remember it or didn't write it down or can't find it in your notes from yesterday, I will write it down. What else will you need? I don't know that I gave you the mass of the moon yesterday, but I will give it to you today. That way, in the future, you will have it as well. What else will you need? Which distance? The radius of the Earth? Because the radius of the Earth, I know that one, 6.37 times 10 to the 6th meters. You don't need that? What do you need? What's that? I can't hear you. Okay, so you want the separation distance, 384 times 10 to the 6 meters. Okay, I'll give you 60 seconds to tell me where the center of mass of the system is. I will write it down, but I will be salty about it. So I better see them pencils flying as I explain. To find the center of mass, you have 2 ways to do so. And you have to do it only in 1 dimension at a time because our system of math only allows for 1-dimensional calculations. This can be considered a 1-dimensional system. Because it can be, we only have to do this once. However, do you take an integral or do you use them as point masses? I said already, you can do this problem as point masses as they are separate entities and we know where their unique center of mass is. So point mass it is. You pick one of these points to be 0. You have to choose a reference. You can make that reference anywhere you want. I could make the reference of 0 to be here, some arbitrary distance away from the Earth. That would be silly and not necessarily beneficial. I would probably want to pick a good point of reference. So how about we pick the center of the Earth, which is what most of you did. So if we start from the center of the Earth, I want to also reiterate, the number has to be between the Earth and the Moon, and they are separated by this amount. So if you get 3 times 10 to the 10th meters, you're wrong. I don't even have to say why, because you have a value that is way too big, right? It has to be a number less than that. So we start by picking our reference point. I'm going to choose the center of the Earth as my point of reference. Once I've made that decision, then I need to choose whether I have to integrate to find my answer or point mass. We already answered that, so I'm going to use the point mass solution, which is a summation divided by another summation. The top one says take the mass of the first object and multiply that by the distance from your reference point to that object. Then add it to the mass of the second object multiplied by the distance from the reference point to the center of that object. And keep going until you get to all the objects, but we only have 2. The bottom one says just add all the masses together. It is a weighted average, with the weight being location. So let's start with the Earth. 0. That is its contribution to the location of the center of mass, because the center of Earth is located at the center of the Earth, which we said is our reference level, our reference point. Plus, next object. What is the next object? Moon. M is 7.3 e to the 22nd. R is 384 times 10 to the 6th. And yes, I find it frustrating and I have to do this. That's it. There's just 2 things. Drop down to the bottom. Add up all the masses. Well, the first mass is 5.96 e to the 24th plus 7.3 e to the 22nd. There you go. But then comes the part where you use your calculator and prove that no matter how diligent you are, there's always a snafu in the plan. And I can have everybody calculate this the first time, and many of you will get it wrong, but not know if you're wrong or not because it's just some big number and you don't know what to think. But the correct answer should work out to be 4.6 times 10 to the 6 meters, making it about 2/3 of the way from the center of the Earth to its edge. All right, now this should bring up a whole bunch of things that we now need to start considering. First, the Earth doesn't revolve around the Moon, and the Moon doesn't revolve around the Earth. They both rotate. So there is a angular speed to this system. So point 1, start considering that these systems could have angular quantities associated with them. And one of them would be an angular velocity. That doesn't take away the fact that the Earth is going around a circle like that, correct? The Earth is in orbit around its mutual center of mass with the Moon. And it must make this orbit in the same amount of time that the Moon makes its orbit, because they have the same angular speed. So the Earth and Moon are both revolving. They both have their own value for V, but they have the same value for T. Again, they both have their own value for V. They're traveling at different velocities. The Moon is clearly traveling faster than the Earth because the Moon is traveling in a much bigger circle than the Earth is traveling. But they have one angular speed. In fact, V equals omega times R still works here. 3, this system has a moment of inertia about the center of mass. And since that center of mass is inside the center or inside the Earth, you would probably have to use a solid sphere for the Earth and the parallel axis theorem to add its contribution to the moment of inertia. But the moon could probably be treated as a point mass for its contribution to the moment of inertia. I bring that up because what if you were asked to figure out the kinetic energy of the system? You could do it two different ways. I mean, you could do 1/2 I omega squared if you knew the moment of inertia of the system. Or you could do 1/2 MEVE squared plus 1/2 MM squared. These should be equal, right? We can treat it like 2 point masses with linear kinetic energy or one continuous mass with a moment of inertia and angular speed. The value would be the same. Which of course brings me to 5, the system has angular momentum. I bring that up mostly because it played such a prominent role in the way our solar system was formed. The angular momentum that existed in this region of space has been preserved and thus is expressed in the angular momentum of its constituent parts. But we still have a means of calculating the period. And you should, at this point, realize we could calculate the period and see if it's much different than what we already calculated. Agreed? So, what do you want to do here? Do you want to calculate the period of the Earth around the center of mass or the moon around the center of mass? It's going to be the same number. I'll help out a little bit. No matter which one of these we do, we're going to get a generic answer. I'm not looking for the number. But this would actually be the radius of curvature for the Earth's motion, while this will be the radius of curvature for the moon's motion. Which one of these do we already know? The yellow one or the green one? We found the yellow one, the distance from the center of the Earth to the center of mass. Do we have enough information to find the green one? Yeah, we sure do. So it doesn't really make any difference. So let's consider some generic calculation here. I'm going to slide all this. Actually, no, I'll just make it all smaller. Put it all up there in the corner. And remind you that finding the period of a circular orbit requires first knowing that we're dealing with circles. I'm writing both of these down because now you understand we could deal with this using angular quantities or we could deal with this using linear quantities, so it doesn't really matter to me. We're probably going to have to use that the net force is actually just one force, M1, M2, G over R squared. And lastly, that this has to do with how fast it's going and how long it takes to go around this circle. All good? All right. There is RS and RC. I'm going to make these kind of clear, I think, that we have to start separating these out. And I tried to use the language yesterday to help us, but RS represents the separation distance, while RC represents the radius of curvature for the path. So can you go back through there and put an S and a C on all of the R's over here? Should be done. S here, C here, and here, and here. All good? So let's do the work real quick, because I want to remind you there's a series of steps here. I would probably find the velocity first. We can do that straight away because we know the net force equals two different things. We can just set those things equal to each other. So I'm going to state that M1, M2, G over RS squared equals MV squared over RC. It's at this moment that you would have to make a decision whether we're finding the velocity of the Earth as it travels in its circuit or the velocity of the moon as it travels in its circuit. Which one do you think we should do here? Because that matters. Moon? Earth? Let's do moon. It doesn't matter. We're not going to plug any numbers in. The reason I bring it up, though, is it determines which m this side is. So if you're trying to take notes so you could do this on a problem that isn't just the Earth and moon, that's the m that you think is moving. So if we're talking about the period for the moon, well, then we would be talking about mm there for the mass of the moon. If we're talking about the Earth, then that'd be me for the mass of the Earth. But that dictates which r we use, which radius of curvature. If we choose to look at the mass of the Earth, we're using the r from the center of mass to the center of the Earth. If we choose to talk about the moon's motion, then we'd use the r from the center of mass to the center of the moon. We good to keep going? I'm going to say moon. There we go. Now what this would have meant is the mass of the moon, which is smaller, cancels out. Mass of the Earth, bigger, stays. Right? But that also means that the r we're going to use is different. But it's a direct proportion. So the change in mass is directly proportional to how big that r is going to be. And so it still works out the same. The direct proportion is built into the center of mass formula. So we get the same number. The same period will exist for both of these. This cancels out the mass of the moon, and it gives us a stopgap. I'm stopping at V for a purpose because it looks different than yesterday. Right? The R didn't cancel out this time. Yesterday would have canceled out. We good to keep going? All right. Well, I don't really want to stop there. What I'd prefer to do is take V away and put something in for V. And that's going to be 2 pi RC over T squared. Right? Replacing V with distance over time. Right there, Edison, right there. That good? Why? Because I wanted the period. I want T. Is that okay? Good to go. So we want T. We want an expression for T. And this is just algebra. So, of course, I cancel out these m's. I'll get mass of the Earth times g over rs squared equals 4 pi squared rc squared over t squared rc. I'm not skipping too many steps here because I think I need to be explicit. So I do want t as a function of everything else. So I'm going to cancel out the 1 rc, and I'm going to do a little cross multiplication and do a little factoring and find that t is equal to 2 pi times the root of rs squared times rc over meg. It's not much different than yesterday. We just had an r cubed yesterday, remember? By expressing it this way, though, what I hoped to say to you is it should be clear just from this expression that our value we calculated yesterday is too big. Can you see why that's true? RC has to be smaller than the separation distance. It has to exist somewhere in between the separation distance. Yesterday it was RS cubed. Today it's RS squared times RC. The top of this fraction is going to be smaller, so the period is going to be shorter. The value we calculated yesterday is not the right value. It's going to be less than 27.4 days, which should still be a little weird that it's 28 days. Remember, 28 days is more about full moon to full moon than it is about how long it takes to go around. What we generally do when we're trying to put something in orbit is we do a two-stage process if we have enough fuel to do so. The first process generally just gets the thing out of the atmosphere and gets it into a low Earth circular orbit. So I made my Earth really small here. I guess if you want more like reasonableness, I should make the Earth bigger. But even this would be too big or too small for this. But either way, we launch early enough and we get the rocket out so that it's now traveling in that circle. The period of oscillation of this orbit is pretty quick. In fact, if you want to know the period of oscillation of this orbit, it's a circular orbit where the Earth is clearly at the center. I don't need to worry about the center of mass. The period here would be 2 pi times the root of r cubed over MEG, where just make r cubed a little bit bigger than the radius of the Earth to account for the atmosphere. It ends up being like 40-something minutes. It's pretty fast. That's why, they're kind of zipping around. They're going around the Earth fast. Space station is further out, but it's not that much further out. The second circle I drew isn't the right size. So, in fact, I'm looking at it now and it's hilariously bad. So I want to correct it. That's not better. I'm trying to make it look like the Earth is in the middle. So that's how all the right proportions. There we go. All right, so the object's in orbit. It's in that lower Earth orbit. Here, 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 here. It stays there. So when the NASA says it's time for us to go to our new orbit, well, you can't just fly there. You have to use a transitional orbit. So right when we're going this way, right when we're here, we want to fly outside this orbit. So we hit the engines right there and speed up. Usually you do it in anticipation, so you would do it just before this moment. But we increase our speed. That means we're going too fast to be in a circular orbit there. And that presses us into an elliptical orbit. Now the elliptical orbit will take us out further, but on our way out, we'll be slowing down. So when we get here, our velocity will be too small to stay in a sustained circular orbit. So we fall back into this elliptical orbit. And we stay in this elliptical orbit until we do something that will make us change our orbit. As you can probably imagine, if you want to do this with the least amount of fuel, you get one try at it, or you wait till the next orbit and do it again. But again, as you get closer to the orbit you want to be at, you speed up here to create a circular orbit at this altitude. You're now in a circular orbit further away from the Earth. Now, the reverse of this process is what brings you back. In fact, if you want to come back to the Earth, you reduce your velocity so that your orbit perhaps crashes into the Earth. And that's what you would do if you want to come back. So whenever we bring something back, we slow it down. And that changes the orbit to a point where it falls into the Earth. Astronauts are not massless in space, and they're not truly weightless in space. There's still a force of gravity on them. In fact, let's do a quick bit of calculation. The space station is, did we talk about what an altitude is? Separation distance is the distance from the center of the Earth to your orbit. That's this distance, say. We're talking about the outer orbit. Altitude is the distance from just the surface to that orbit. So if I give you an altitude, you'd probably have to add the radius of your planet in order to get the separation distance.